Jeremiah is CRO of Verusen and is a native Texan whose first job out of high school was as a roughneck on the oldest drill ship for Diamond Offshore. After finishing his computer science degree, he focused his career on asset and maintenance technologies for the asset-intensive industries. For the last 15 years, he has supported clients such as ExxonMobil, DOW Chemical, BP, BHP, PETRONAS, ADNOC, PDO, Total Energies, TC Energy, and many others. All right, audience, you're here for how to leverage AI to help define spare parts criticality methodology. Jeremiah, take it away.
Yeah, hey, good morning, good afternoon, wherever you may be in the world. I'm going to turn my camera off so for bandwidth purposes and just to so it's not in the way of the presentation. So bear with me 1 second here. All right, let's jump into this exciting world of spare parts criticality. So real quick, I will go through who Verusen is, talk about the MRO inventory optimization problem, and then how do we address that through spare parts methodologies, criticality methodologies for spare parts, and then how we leverage AI and how you can leverage AI to really use these kind of disparate data sets to determine what is critical, what isn't critical, on an effort to get a proper stocking strategy, which all of this will be tied to production and uptime and so forth, which I imagine most folks on this call or most interested in around from a maintenance perspective. So who Verusen? Verusen, we're an AI software company. We've been in business for a little over 8 years now, building an AI product that is purpose built to solve MRO inventory optimization. Out of this, what we're doing and what this is, just a rudimental level, is we're pulling out your master data catalog items from your ERP or your EAM software, and then we're pulling all the data that goes around that, issues and receipts, bill of materials if you have it, and it's going to get fed into our system. And some of the use cases that will come out of this are going to be capabilities to really identify like parts across all your plants. So if you've got a lot of our customers are global customers with plants all over the world, and so the large language model that we've created in the system has been really purposely built to train to look at this poor data descriptions on parts and really determine, hey, this is the same bearing. You're using the same bearing at 4 different plants. It's all named something different, but it is the same bearing. And then it allows you to help better stock, buy, look at price variances, criticality, what we're here to do today, and then look at network, and then the capability to do network and sharing capabilities within the system. Bear with me 1 second, I have little user problems here, but all right. So just to a little bit further down the rabbit hole with what the system is doing is, so we plug into typically your ERP and EAM. So a lot of our customers are SAP, some Maximo, some Oracle today. And what we do is we pull all that transactional data. So it's very data hungry. So lots of that work order history, procurement history, issues, receipts, bill of materials. What that's going to do is go into a large language model that we built. And we're going to talk a lot about that today. But what it does in that large language model, what it's going to do is help really identify. It's not built to cleanse the data. It's built to identify where you've got data gaps and where you have good data sets and help to enrich those data. And then ultimately what it does once you push down to that is it's going to start now, once it can identify, hey, we've got these bearings are all the same bearing. Here's what the criticality should be for these bearings. And that's what we're really going to talk about, that methodology and how we approach that, how to approach that in general as well. And then what it's going to do is go to a probabilistic AI to make a stocking recommendation. So in that bearing example, you may have it at the warehouse level, and you may have a min-max of 10 and 11. The system's going to look at it and say, for this example, maybe you've only used it twice in the last 24 months, and you've got 10 of them on the shelf. And when you use one, you reorder one. So in this example, it would be, maybe it's a critical bearing. It's used on a critical A piece of equipment. So we'll lower it. The recommendation could be a 5 and a 6. and the user would hit accept, and it'll push it back into the residing ERP. So that's the general premise of what Verusen is and does. Now, talking about the large language model, we've been building this for 8 years, over 8 years now, about $25 million in investments to get this thing operational today, with over 30 million master data SKUs ingested into the system to train it, and then 6 billion transactions, individual transactions around those SKUs to train this model. And the idea, again, is really trying to help anybody that's been in these industries for years, or to any extent, will know that a lot of the data sets from customers' data, from catalogs, description of these parts, is really poor. And that's where this AI model really kind of can shine to help pick bits and pieces of the puzzle and put this together. But let's talk about overall the big problem that we see time and time again. In my experience, worked with a lot of asset-intensive companies around the globe, and when they set their stocking strategies, their min-maxes, their reorder points, their criticality, this is really done typically, my experience has been done at the initiation or the startup of the asset. So reliability teams will go and do an analysis. Say you've got a pump, that pump is really critical. They deem that this is critical. If this pump fails, production is shut down. So great. So now how many, what are all the components? And sometimes they create the bill of materials, sometimes they don't. As you guys know, if you actually work for the end customer, this is haphazardly done in most cases. But if you do know the parts that make up that pump, the bearings and so forth, you'll also, what the reliability team will do is an analysis on how often they're going to do a PM study, do a PM, as maybe they replace that bearing once every year or two, on top of whatever service goes with, like greasing or what have you. And then that's how they'll determine the stocking strategy. We need to stock for the next 3 years for operational. But typically what happens here is it's very much kind of like a finger in the air to figure out, kind of directionally where they want to be. And they typically overbuy 2 to 3x at that point. It's not a very mathematical approach. They're not looking at, the size of the warehouse or the lead times and how many suppliers can supply this. Really purely is for looking at it from an operational standpoint, how often they think they're going to use it and how many they need to keep. And that's what they go by. And this was what leads to really poor surplus inventory over time. So with that said, that's kind of describing the problem. Now I just want to really get rudimental and talk about the methodology of criticality on spare parts. I guess I'll give you a real world example. So at one point in time, some years ago, I owned a 97 Chevy Tahoe, and anyone in the US will know, or North America, or even the Americas, and these things are mass produced in Mexico and Canada and US. You can drive to any parts store in the US and pick up parts, most of the parts for this thing. I had a buddy that had a 1987 Porsche 944. Both had fuel line leaks and they needed to be replaced. So like I said, I could drive to my parts store. I could get that fuel line within an hour, however long it takes to drive to AutoZone, and however far AutoZone is from where I am. He had to special order this from Germany, and it was a turnaround time of 6 months. Now we both can agree that that fuel line is very critical to keep that asset, that piece of equipment up and running. I can't drive my Tahoe without that fuel line, and nor could he drive that Porsche without it. But the sourcing and the procurement of those fuel lines are very different. And that's what we're really talking about here today, how to come up with a methodology, how to use AI to really rationalize some of these decisions and not make everything critical. So as a maintenance professional, and in my background as well, when I was a roughneck, I did do quite a bit of work as a outdoor machinist after becoming a roughneck, and worked on a number of turnaround shutdowns in Southeast Texas, where I'm originally from. And our job, when you're doing it, shutdown turnaround is different from like where there's a break fix. But the job of the maintenance team is to keep the assets up and running. So whether it is a shutdown turnaround, you're overhauling a bunch of equipment, but if there is a break fix, your job is to get that thing back up and running as fast as possible. And so you'll have influence on what the stocking policy is, but it's not your job as maintenance teams and operations teams to source that material. Typically, it's material management and procurement. And what we see time and time again is these things are operated in silos. And compounding that of the silos is it's almost impossible to rationalize stocking strategies on a routine basis. And what I mean by that is that a lot of our customers are managing hundreds of thousands of master data item SKUs, individual parts that they routinely buy or barely buy on occasion, maybe slow moving to fast moving. But the idea is that the problem, not the idea, but the problem statement here is that it's almost impossible to go through these catalogs on a routine basis and determine, is anything changed in that stocking strategy? I'll give you an example. So if you've got that bearing, and maybe that bearing was from a specialized pumps, a centrifugal pump that was, very used in corrosive material, and the bearing was protective coating. I'm just making this up on the fly, but and you have to buy that bearing from the OEM that makes that pump, and your lead time may be, like 10 weeks. But all of a sudden now you can source that bearing from Granger, and so your lead time's like 1 day. These are the variables that would impact your stocking strategy, would impact your criticality. And that's what we're going to talk about. Is this is a really tough problem to solve for without technology leveraging all the disparate data that's being generated from work order history to bill of materials to purchasing data, to really try to put together clear recommendations for teams to rationalize some of this. So let's just jump into the meat and potatoes of how to automate this and methodology around criticality. So first off, what is criticality? So I imagine most people on here understand that criticality, really the rudimental is coming from the asset equipment criticality. So most of the industries that we're operating in today are regulated, and they're required to have some type of health and safety and criticality methodology defined for their critical equipment. Now, a good example is like the nuclear industry. If I recall, it's been a while. The nuclear industry is going to have like a 3-system failover. So I've got you've got several inline failovers, and then you've got to have this, the spares, insurance spares in the warehouse, and you have to prove it, and you have to have a methodology to define that. And so this is in upstream oil and gas to chemical manufacturing, process manufacturing, food and beverage. To some degree, I'll have some of this regulation where they have to define the criticality of those assets. But what we see in a lot of cases, when it gets down to the spare parts, it's not done as well. So what I see time and time again is it's a binary. So it's yes, it's critical, no, it's not critical. And in those scenarios, what we see a lot when it's binary is like everything's critical. And when everything's critical, nothing's critical. If that makes any sense. And then another, when just a step above the binary is ABC criticality. So just assigning an ABC code that's static. So this is better than, in my opinion, than the binary, but it is static. So it's not dynamic. It's not taking into account, like the example with the bearing, where you flip from an OEM now to multiple suppliers where your lead time drastically dropped. I come up with a bunch of different reasons, but ultimately, when you have these methodologies, what this does is it introduces risk to the business, because we talk a lot about reducing surplus, but it can also introduce risk in the sense of, let's say that when you stood up an asset 10 years ago, and you were able to source some of these parts from multiple suppliers, and now this asset is aged, no one's really carrying some of these specialized parts, and some of it's maybe custom built, and now your lead times are extremely long, and you don't know that until you have a break fix. So having some of these dynamic tool sets to help leverage criticality is really important, to not just for surplus, but also downtime reduction as well. I'll just go to the next. So build this out. So how to pull in, how to automate this process, but also break down the silos between maintenance operations and procurement, supply chain, material management teams. I've seen this time and time again where what we do is we will do a criticality workshop with the customer. And what happens out of these workshops is sometimes it's the first time these teams actually sit in the same room and actually discuss some of this. And it does get a little bit heated in certain situations, but I'll just walk you through an example of what this means and how we at Verusen leverage this data set. So you've got up here, what you're going to see is a bearing used on a hammer mill. It's a pillow bearing used on a hammer mill. Now that hammer mill is the equipment, is the asset, and is deemed B in the EAM software system by operations. Now we're going to look at all the data that's available in the software, from your ERP to the EAM. And if you look at the master data catalog for this material, for this bearing, we may get the material type, maybe not. We'll maybe get the commodity code. Will we get a criticality flag in that scenario, like a binary flag? Yes, it's critical. No, it's not. Is it related to safety or environmental health and safety? How many suppliers? Average price? So all of this can be variables to determine how critical it is. And then also this is important from the AI perspective because it's training on this bearing. So when you do have another plant that has the same bearing, that you don't have material type or commodity code, but you do have a decent description, then that's where the AI can start leveraging some of those data gaps and enriching the data. But moving on, so now once we understand the material type and some of this base data and where the gaps exist, then we can start looking at where's the bearing been used historically from work order history and bill of material data. A lot of our clients don't have good bill of materials, so work order history has always been a really good source to assign criticality. So in this example, this bearing has been issued on this hammer mill, and the hammer mill is a B, so we're going to adopt that B criticality in that example. And now, so the B, and so my understanding of this B was most likely it's a hammer mill goes down, it's a B, not an A item piece of equipment, because it's not going to shut production down, but it may just reduce capacity. And so this is now a B piece of equipment, and thus the bearing is a B as well. Now, if we go look at the procurement, so let's say in procurement, how many suppliers can we get this from? What is the lead time? Can it be expedited? What are the holding requirements and regulatory requirements of this item? And what we come out of that and what data is available in the procurement systems, what we find is there's multiple suppliers, there's a very short lead time, operational risk is going to be less, so we move it to a C. And all of this will be tied to a service level and a stocking strategy. Hopefully that makes some sense. Normally when I do these presentations, it is with a team, it's meant to be open dialogue. So hopefully if you guys have questions afterwards, happy to revisit it if I'm going too fast. But with that said, I think this is a good way to maybe visualize what this kind of looks like in a logic gate scenario. Now, I'm explaining this to you to build into how we use AI. So this is an actual customer, and this is the rules that we, out of a workshop, is a rule set that we walked away from and configured into our software system. But it's important to know that what we're doing here is we're walking away with a rule set that we're training an AI model on that learns from these models. And I'll explain that in a minute. But I'll explain what you're looking at here. So the PSV, pressure safety valve, pressure relief valve, in this example, they dictate one of they're tied to health and safety, and environment and safety as well. They automatically skip go and go straight to A. There's no other rules to consider. Is if they have a material commodity code PSV or PRV, they automatically just go to A in this example. Now, when you step down a level, it's the system, the intelligence in the system is going to look at, okay, there's a criticality indicator. Do they have a yes, it's critical, or no, it's not critical? And they had a binary system. And so in this example, it was critical, and it had been used on an A or B item on a work order in the past. And you can only get it from an OEM, single source. So it is an A. And if you step down one further, you'll see the only difference between the next one is that it was deemed not critical by maintenance, but it had been used on an A and B, and it was single source. Now it's a B. This is what the maintenance teams and supply chain teams agreed to, as far as now walking away from the workshop, this is what we're going to train our AI on. And just another example, just further down. So now you can see a little variation here where now we look at it is critical. It was used on A or B, but you can get it from multiple suppliers. In the first example, the lead time is long. Now that was a description that we put in here for this presentation, but the lead time is long in their example is anything over 30 days. So it's important to remember our software is actually calculating a moving average lead time. It will take your stated lead time, but it is calculating a moving average lead time. So it's going to give you a more accurate actual lead time to consider this as well. In this example, for the next one, the only difference is the lead time is short. And in that time, and they were saying anything under 5 days is considered short. So that's a C item. So this doesn't have to be your rules. This was their rules that they agreed to, and we took those rules back, and now we apply them to the configuration, and we train the AI models going forward with those rule sets. So the AI models will know what is really important to this customer and their data. It's just to go into this a little bit more detail. So again, here's the critical B hammer mill. And here's all the parts. So you can see there's couplings and the bearing. The bearing, we walked through that C analogy, and you get some screens that are B, and it's because it's a single supplier, and the lead time is medium, if you will. But the hammers, so the hammers are a special construction. They're custom built, long lead times, are expensive. So in this example, we mark it an A. Because, again, for all the reasons they say, and that's pretty straightforward even when you're training AI. But as things change, if you're in this industry and you know this, that things always change. In this example, let's hypothetically, I'm a user in Verusen today, and I disagree because I just found out that I can now source these hammers from Grainger, and my lead time is now a day. And this thing needs to be a B. Now, we don't have that data in our system yet because they haven't went and bought it from Grainger. They did, in this hypothetical scenario, I just found out about it. So I can go in and I can tell the system that it is a B item and why. And this is what's really important. We do, it was what we call users in the loop with the AI model, is that we're training that AI on other knowledge that's not in the data, and this is a perfect example of that. So where they say it should be a B, then we're going to ask them a series of questions, why? And then that trains that AI model for going forward. It's going to know that these hammers can now be sourced from multiple providers. The lead time is no longer as long, and it's going to start making those recommendations across all the operations. And now it is up to the users to agree. It's not automatically going to, so let's hypothetically play that scenario out. Maybe that's only in the US that you can get those hammers from Grainger, but if you got plants in, say, Indonesia, they can't. It's still a custom sourced, long lead times, very expensive, or they have to buy it from Grainger. It's cheaper, but the lead time is still longer than what the US plants are. So all those factors are going to go into those models to really help try to determine, is it still really critical or not. In addition to that, what's really neat about using AI in these type of models is that in that scenario, I was saying that the user, say the material manager, found out that they could buy this hammer from Grainger now and not the OEM, or have it custom built. And so, they knew something that the data and the AI did not know, and they informed the AI, trained the AI going forward. Now, if they didn't know that, so maybe Grainger now is offering this, and the user wasn't aware, but the procurement team found out it was now available in Grainger's catalog. They went and bought it, and in that purchase order history made its way into our system, because we're going to be pulling that on a regular basis. So when we pull that purchase order from Grainger for this hammer, then we're going to pick that up, and we're going to see that hey, you're no longer buying this from the OEM, and your lead time just drastically dropped, your price dropped. This is no longer fits within the B criticality methodology, or the A criticality methodology, and should be demoted down to a B, thus impacting your stocking strategy. To further that, to talk about where this large language model really comes into play here, and really, in my opinion, can really start benefiting um, our customer base and the broader asset-intensive industries out there, is really like I've described, looking at those short and long descriptions. And anyone that's in these client sites or been around this is poor examples of from material management to maintenance guys can't find the part they need, so they add the part, and you add duplications over years, and you maybe you likely already have the part in the catalog, but you're still you're creating a new item so you can just go buy it because you need it, whatever the case may be. This large language model, what's really neat about it is that it's been trained on all these abbreviations. So in this example, you see 3 plants: Atlanta, Charlotte, and Greenville, all 3 AC motors. And what you see is that 2 of them are the same and 1 is not. And so, but you can see the abbreviations like MTR. Let me back up here real quick. And a motor spelled out completely, and then a misspelled motor, MOTR. So the AI is smart enough to know that these are all AC motors, and then it can look at the abbreviations for amps, RPMs, and determine and basically categorize these things appropriately, like they should be, and say, hey, these are in Atlanta and Greenville have the same 2. They're not named the same, but these are the 2 same items. Okay, great. So now we've identified some duplicates. So in my experience, most of my big customers have the ability to already have scripts to go do something similar to identify duplicates. There's a bunch of different tricks. This isn't rocket science. But then where it really starts getting interesting is the AI is starting to promote better buying strategies. So, hey, your Atlanta plant is getting it from Granger for $32,000, and we've got a good criticality, and it's on a bill of material, and it's been used on a critical asset. Where in Greenville, they don't have those data sets, because let's face it, and there's a lot of cases where we see poorly implemented EAM systems where the work orders, they may be issuing it to a work order, maybe it goes into a black box. I've been on many customer sites where they're just replenishing and they do cycle counts, and that's how they run their inventory, and maintenance just comes and gets what they need. So all they really get visibility to is just the procurement cycles of say this motor, and you know what you're paying for, and it's off contract. So there's a lot of opportunity here to reduce your spend and enrich your data on criticality, because I'd be willing to bet if you dug into this Greenville plant, and if this motor is an A critical like it is at Atlanta, they're probably got a number of expediting orders for this when it does fail, from just a poor planning and execution piece. And that's really kind of the beauty of this large language model, being able to look at this all holistically and finding where the data gaps exist to help enrich those data gaps. So now we talked about just back to the process. So where the large language model, how it's applying to criticality. What I'd like to do is talk a little bit about now from a probabilistic AI standpoint. You've gone through this effort. You sat down, you did a workshop, you defined some methodologies, and now you've got an AI model making criticality recommendations on your inventory, on your spare parts inventory. Now, at the end of the day, one of the big reasons to do this is to determine, are you holding enough inventory for your critical spare parts, and are you holding too much for your less critical spare parts? And that's where the probabilistic AI models come into play. So this probabilistic AI model, the idea behind what we're doing with this model is that it's going to be calculating a moving average lead time. It's going to look at order history, work order issue history, bill of materials, criticality, and service levels. So one of the things that you'll do is in these workshops, we'll determine is we'll give you an estimated what your actual service levels are for each of these items. And if you understand what service level means, but just the definition of service level, was it available when maintenance needed it? And so, if it's 99% available when maintenance needs it, then that's if that's what you're targeting. But you can play with those service levels based on how critical it is. And that's really the intention that we're trying to drive out of this. So what the probabilistic AI is going to look at all those different data factors and then give you a stocking recommendation. So you may have on the screen here, you may have 20 and 40. it may say it's 18 and 24 based on all these different factors that you have in your data. With that said, let me just bear with me 1 second here, and I'd rather just show you the real software versus a screenshot. So this is Verusen itself, and I know this is meant to be a criticality, but I want to articulate the value of going through all this effort for defining a criticality. What's the output? What is the ultimate goal here? And in my opinion, ultimate goal is, as the the companies that we all work for, we're fiduciary responsibility to some degree on making sure they're buying the right stuff, not overbuying, and we're operationally correct and keeping things up and running. And so that is ultimately, if you go through all this effort of putting together, even if you do this manually and define your criticality manually, routinely looking at and applying those rules to those spare parts is the purpose, if you will. So what I am going to show you is an example of one way you can go about leveraging those rules and that methodology to optimize your inventory, whether it be Verusen or some other or building something. But what you see on your screen here is an actual customer with about 7 plants across the Americas. And what you'll see is that you have verified and unverified. It simply just means verified is they've approved the recommendations. Unverified means they haven't. So if I go into unverified, you're going to see a list by highest value of what we call cards, but recommendations, essentially, recommendation cards. And in this list, you'll see this one's at $32,000 value. And really what that calculation is just the difference between what the current stocking policy of inventory they have versus what we're recommending. But as a user, as a material manager, or even maintenance operations, what I would see in here is the intention is to bring all this disparate data into one visual screen and experience for a user to quickly make a decision. And one of the KPIs that we're tracking as a company that's really important to us is the longer the customer's in the system. So not on a daily basis, but the longer the customer is a customer of Verusen. So we've got customers that have been customers for 4 and 5 years in the system. That time, their individual user time in this system continuously drops, because what we're doing is we're not implementing the software, we're training an AI model. And the more confidence you build into this software, the less time your users are actually in this software. And that's really important. And why I say that's really important is that if you think about traditional software, it's the collecting data, form capture data. You think about your ERP and EAM software. All they do is they build a bunch of forms to collect data to go into a relationship database, and they give you some BI reports. We exist because of those systems do a poor job of putting real data analytics behind this. But without getting on a soapbox and a tangent here, our whole purpose of this goal is like we really want to try to co-pilot and help your materials managers, your supply chain teams optimize their inventory, but not be spending hours on end in a system trying to make a decision. We really want to train this AI model to help make quick, fast decisions. So in this example, what you see here is this client has it's a critical B item. It's a motor. It's an AC motor, and they've got a min-max of 20 and 40. We're recommending an 18 and 24. So if you just kind of dig into it a little bit more, you can kind of see this thing's been issued out over the last 2 years, about 17 times. And it looks like maybe they did some type of shutdown turnaround here, and there was 12 of them issued out at this time. But we're not putting anything at risk. They've got 23 of these things on hand, and your lead time is fairly long lead time, the average lead time. So what's stated is 43, and this is an SAP client. The average is 23 weeks. And so if the user agrees to this, they simply just hit agree, and then that min-max is going to get pushed back into their ERP. But if they wanted to explore a little bit further, just really try to dig in and understand where their gaps sit, and do they agree with this? It is a B item, and this is, as you can see, we are going to show you, if you recall, through the rules that we set and train the AI models on, it is going to give you a perspective of what the A, C, and D would look like, and what the service levels and what the stocking strategy is. So even if you went to an A item, you're still lowering that quite a bit, and that's still at a calculated 98% service level. So even if the user was like, hey, I don't agree with this, I know something that the data that's not in the data and the AI doesn't know, you can come in and disagree with this, and then you can put in what you think the min-max should be, and then what your reasoning is. And then that's training that AI model on the knowledge that the tribal knowledge that we know that exists in all these maintenance organizations around the globe. And that's where it starts to encapsulate and learn more about this inventory. Now, I will say it's also important to know, and in my experience, and from time and time again, that there are companies out there with people out there that are doing that have poor or bad business practices, and they could potentially have the opportunity to train this AI on their bad behaviors. And so we do have another model running in the background to capture that. So if you have a user constantly disagreeing with recommendations, that will get flagged and that will be reported on. So every bit of this is tied to workflow. So for this example, this is a B critical item that I showed in a minute ago. And so with that being said, since it's a B item in this customer, they have workflow approval processes tied to all their A's and B's. So any A and B recommendation, increase or decrease, has to go to engineering to do the final approval. So typically a supply chain analyst is using this software, they will hit approve or disagree in whatever they put in, and that's going to go through one more approval flow before it makes its way back into the ERP or EAM software system. Beyond that, then you can get into, this is what I would say is your crawl, walk, and run type approach to assigning criticality, optimizing inventory. But then building on top of that is then you can go into what the system has with the AI capability is doing modeling, network modeling. And what I mean by network modeling is that you can have most of our customers have many warehouses. In certain cases, we have customers that have multiple warehouses at one plant, or they have plants that are somewhat clustered, plants that are in a certain state or a certain region. And in those scenarios, I'll give you a good example, offshore drilling contractors. So they are traditionally, so think of like the Gulf of Mexico, they could have 6 drilling rigs in the Gulf of Mexico, and they're gonna have one shore base, but they're not typically traditionally set up to be a hub and spoke methodology to share that inventory. It's a very complicated problem. And now what we've done with our probabilistic AI models is we can simulate these hub and spoke methodologies. We can simulate the multi-echelon models in the system to help the customer determine what is the best model. You're not going to want to share every item. You don't want to share in highly critical insurance spares because some plants may be really old to a new plant, and the really old plant you've got 2 of these insurance spares. There's no one else is making them anymore. You've got to have them. You're not going to share these things out. Versus you may have some real high turnover, highly used items that are fairly expensive. So we have models you can plug in parameters like I only want to share something that's a B, C, D, and E, and it's above $1,000, and it will come up with a simulation of all the items that could fit into that scenario that have a good trend, and then it's going to look at where each plant has a demand and another plant has a surplus, and it help you rationalize where you want to transfer and ultimately get to the centralized hub and spoke methodology. But all of this, I say all of this, and to say that it is all hindered and tied to criticality. You can't do any of this without knowing how critical things are. And I'll leave you with this last analogy before we open up for Q&A. Is the best way I think to describe this is, in my opinion, is there's a lot of tools out there that come from, that have algorithms to optimize inventory. And a lot of the methodology behind this is looking at procurement history. Absolutely, we can apply a procurement history to any bit of this data transactions, and you can go look up trend seasonal, Crustons. There's all these algorithms off the internet that will give you a stocking recommendation based on procurement history. But the problem with MRO is, simply put, is that it's lumpy usage. It's very hard to predict. It's not like aftermarket and finished goods. And what I mean by that is that, giving a good analogy, if you're in the grocery store, and the grocery store runs out of bread, running out of bread doesn't shut the grocery store down, doesn't potentially kill somebody. Grocery store keeps going. They just call their vendor and say, hey, we need some more bread. Can you get it in here ASAP? We're going to miss some sales. In the industries that we serve, we have inventory that shuts production down, and in some worst cases could potentially kill somebody if they don't get the thing back up and running in time. And so it's really important to be able to not just apply like a probabilistic AI to movement history, but also understand, hey, this thing's really, really critical, or this thing's not so critical, and then come up with some logical reasons tied to your stocking strategies. With that said, I've rambled on for now 43 minutes. I'm 2 minutes, and my goal is to get to 45, and maybe I went a little bit fast, but maybe open up for a Q&A. And I don't know if the moderator, or do I need my apologies here. Is she coming back on? Robin, are you coming back on? Maybe not.
I am. I apologize. For some reason,
no
my mute button didn't want to come off. Sorry about that.
No worries.
We do have some questions for you.
Okay, great.
All right. So the first question we have, do stock levels need to be reviewed if you have identified common spare parts in your materials?
So I'm just going to read back what you said. Do stocking levels need to be reviewed if you have common spare parts in the material? So like duplicates, is that, I assume that's.
I'm going to defer to you.
Yes. So if I understand the question right, absolutely. You absolutely want to review stocking levels. Ultimately, look, we claim the big claim to fame for our software is to help reduce surplus inventory. And in that example, if I understand the question correctly, is you're going to have, if you've got common parts that if they're duplicates or identical parts that are just on the master data catalog, then you've got multiple stocking of the same item, you've got surplus. Now, it's really important, though, when you look at tools like this, is how they look at that data set. You want to make sure you're not just saying, okay, we've got 2 items that's held in the warehouse, and we got min-maxes on both of those items. Let's keep this one and get rid of this one. But don't get rid of that history. You need to merge that history, because that's the consumption. So you could screw up your stocking strategy because you're buying and using 2 items. Hopefully that makes sense or answers your question. And if it doesn't, please reach out to me, and I'm happy to elaborate. I'm available on LinkedIn or anything like that. So sorry, go ahead, Robin. What's the next one?
The next question is, must equipment criticality be aligned with spare parts criticality?
Absolutely. To me, one of the best weather vane, if you will, for an analogy, is using asset criticality as a starting point for spare parts criticality. So to me, if you know if you're trying to determine how critical that spare part is, you have to really understand how critical the asset that spare part's used on as your first pass. And then you're looking at, like I presented in here, is how procurement, how easy is it to source? I mean, it's not rocket science. It's really just how, if this is used on a really critical piece of equipment, is it really hard to source? And is it really long to get it to the maintenance people? And if it is, then it's really critical on all levels.
All right, and we have a lot of questions. I'll try to get to as many as I can. Thank you, everyone, for your questions. Is your software system a standalone system, Jeremiah, or does it work in conjunction with Fluke eMaintenance inventory system?
It's standalone. It's standalone. We are partners with Fluke, and excited to be about our partnership, but we're agnostic when it comes to EAM and ERP systems. We have many customers using many different systems, and even customers that they could have SAP, they can have eMaint, they can have Maximo, in all their different plants. And this happens time and time again through acquisitions. And that's another big benefit of our system, is being able to be one source of truth, pull all that data into one system to give them some rationale of their inventory globally.
All right, next question. How do you provide service if a company requires your spare parts criticality assessment?
Workshops. We're happy to come on site. Obviously, those workshops are only really fruitful if we can get your data, because the workshops are tied to the software, if that makes any sense. Meaning that if we can get your data and output an extract of your data, and ideally 3 to 5 years of your data, we'll load it into the system. Then we come on site and we do typically workshops about 3 days. Come on site, run the workshop with you with your data, and then we can output just from that workshop. We can output the criticality, assign the criticality to the spare parts, and give that as an output.
All right. Let's see where to start. There are so many of them. Let's see. How does your tool account for a lot of facilities not keeping track of parts usage or crediting usage to their assets?
Yeah, I'm actually in Brazil right now, about to go into a meeting tomorrow with a big chemical company, and half their plants are missing issue data they have all the procurement data, and then they're reconciling. So in that example, there's a couple of different tricks that we can do to make to leverage this. And one trick is, so from a pure stocking strategy, we can look at when this company does physical cycle counts on a monthly basis, and that's where they reconcile their inventory. And we can say, hey, this is the historical data, that's the consumption history, to train the algorithms on making a stocking recommendation. But when it comes to criticality, if we don't have the issue data, that this bearing got issued to this pump, and that pump is really critical. And if that's in your question, if we don't have that data set to determine that bearing's used on a really critical equipment because maintenance for whatever reason isn't using their work orders properly, or it wasn't set up properly for whatever reason. And in that example, what we can put in rules in place that we know this supplier, or it's an OEM, if it's coming from an OEM, the lead time is X. That's what we would call a supply chain criticality methodology. It's not always the most efficient way, but it's a great way to start. And then second to that, it's good we can leverage other plant data on there. If you've got other plants that got good work order history, that that AI model can make recommendations based on those data, that historical data too.
All right, let's see. Here's a long question. Using motors as an example, different motors will have the same parameters, but different configurations that may differ. How will it be verified before purchase?
Well, that's a really good question. I wish I had my reliability guy here. We were discussing this just yesterday in an example. One of the things that our AI model has the ability to do, so I think some of these examples are a little oversimplified on, hey, these are the same motors based on these descriptions, but you bring up a really good point on you have different configurations. We do have within the system to say this is a replaceable part, and here's a replaceable part. So I know in SAP and other EAM systems they have like parts. We can pull those data sets, say these are like parts, or these are unique. But that in those scenarios really depends on what data is available. But I will say what's really cool about the AI piece is that if you have any ability in, if this is the motor, the amps and the currents, the ampage and the speed, the RPM and the horsepower are the same, but there may be a slightly different spindle or whatever may be on it. It's not exactly the same. The AI will learn from that when it makes that recommendation, you can say, no, this is different, and then give a reason, and then you are training the AI model going forward. I don't know if that answers your question, but.
All right, I have three questions that are very similar, and I have a feeling when you answer the first, it's going to take care of the other two also.
Okay.
So here we go, another long question. I have an older CMMS system that I don't think would communicate with this program. We are planning to upgrade, but could we use this software by manually inputting data, or does this need to communicate to function properly?
Yeah, good question. Um, so no, our system is not a transactional system. We're not creating anything as we stand right now, meaning that you don't create cataloged items in our system. What I would ask is the base data that we need for this thing to work is a master data catalog and an internal part number with any type of receipts. So we can optimize based on procurement, but if you really want to take a route of, like what I'm walking through with criticality and a very, hands-on type of approach to inventory optimization, getting the work order history data where the parts have been issued on the work orders, and leveraging what data sets we have. But I will say, one of the cool things about the large language model I didn't mention today is that in that CMMS analogy that you say, maybe I'm assuming you don't have a parts catalog and you have some rudimental inventory, but you're not buying off a parts catalog. You don't have, I've seen that a bunch of times. Maybe you're doing P cards or buying on demand or free text purchase orders. We can take unstructured data, and our large language model can make sense of unstructured data. So I'll give you an example. In this, on the screen here, this motor, maybe you're buying this motor on a free text purchase order. If you've got some basic descriptions in that unstructured, in the free text purchase order field, a lot of examples we see all the time is in the free text purchase order, they'll type in what they're buying, or they'll have an EDI integration with with Grainger or the other providers, and it gets fed into that description. We can take that and look at all your free text purchase orders over the history and say, hey, you've been buying this motor every 6 months on free text purchase orders. These are the items you need to catalog and create. So we can help stand up if you're moving to a bigger enterprise EAM system, if that makes sense. But it's hard to answer that question. It's not as black and white. I'd need to know what data they do have available to truly answer that in detail.
All right, and the next two questions were both about the ability to enter data manually. Does the system accept data manually entered?
Like I said, you're not creating data in our system. We can input, so we do have some customers that will provide like Excel sheets for faking some movement history wherever it may be. So we have customers that operate, say, in Canada, and during the up in the Arctic, and when it's freezing, that some operations have to stop or cease to work, and so we have the ability to ingest Excel sheets to versus where they don't have work order history and so forth. So it just depends. Again, not a clear answer for them.
All right, next question, and I hope I read this correctly. For materials with a lot of source vendors, do you factor in the quotation cost in the criticality conditions?
We can. So any data available from the procurement system, supply chain, materials management, or work order history, we absolutely can. So, so for example, we're calculating an average lead time of your supplier. So if it's a preferred supplier, we're going to be calculating the moving average lead time of the receipts of those purchase orders. But if you want to make sure you capture total costs, like your quotation cost or cost to cut a purchase order, or the total lead time, not just the supplier lead time, but the put away time, or the review. If it may be a really expensive part, it comes in, it doesn't mean it's immediately available. Your maintenance teams needs to inspect it, make sure it's operational before they put it on the shelf. You can include those or data points and configurations that can be set up in the system.
All right, we still have a few more minutes if you don't mind answering a few more, Jeremiah.
Sure.
All right, so how does your tool account for facilities not keeping track of parts in a standard method, such as one plant has a good BOM and defined asset criticality, but another plant does not, but they're using the same parts? How does the AI model take this into account?
Well, and that I mean, that is my use case that in my PowerPoint, exactly my use case, and that is the power of the AI model is really, and what we see time and time again is our customers will have good maintenance practices. And when I say good maintenance, it's not to slag the maintenance teams. They may be stellar teams in keeping everything up and running. They're just not, maybe the EAM system wasn't implemented properly, or it's just hard to use, whatever reason. The CMMS system is poorly used or not used at all. And then you have another team that's more advanced using the systems like they're supposed to be using and executing, where you have good data sets, like you said, asset criticality and work order history. So that's where the large language model comes in place. So these are the same parts, these are the same items. This one's really critical over here. You don't have any work order history over here, and then apply, use the data you have to apply those same criticality methodologies and stocking strategies at the plant that has the good practices. And then we can push that back into the EAM, the ERP system as well. And when I mean push back, not just the stocking strategies, but the criticality, our lead time, any of that stuff that we're calculating can be pushed back.
All right, we have time for one final question. What if you do not have good asset criticality defined?
Yeah, so like I said before, and this is super common, we see this time and time again, where they, maybe they have some real basic level, or they don't have anything. So what we would do is in the workshop, we would agree on a number of rules. So for instance, we know that all of our critical parts come from this supplier, or all of our parts that are OEM that we have to source from an OEM, they're critical A. And this, again, this is what we would call a procurement supply chain criticality methodology. And so meaning that we're going to assign rule sets based on what data we have and what we know. And we know that these sources, anything with a lead time more than 60 days that comes from this provider or this source, or anything that's above $1,000. If we're buying something above $1,000 or $10,000, then it's likely really important to maintenance operations. And so it's not the best approach, but here's what's really neat about this approach. So let's just say in that scenario, we don't have asset criticality, but we want to get asset criticality. And we're about to maybe upgrade to the latest and greatest EAM or ERP system. We're about to, for Fluke, you may be implementing eMaint and the newest eMaint, and part of that process is going to go through a Formica process to assign criticality to your assets. So our software has the intelligence to say, okay, well, here's what, right now it's a supplier, but once the asset criticality data comes available, then it's going to reevaluate those criticality methodologies and make new recommendations.
Well, thank you, Jeremiah, and thank you for an amazing presentation. And to our audience, thank you for all of the very positive comments I see coming in right now.